Myself Dr. Deepa Vijay Ramane. I am from Sinhagad College of Science. I welcome you all to EPG Pathshala. Today we are going to talk on module Optoelectronics. In this module we are going to talk about LED, that is light emitting diodes. You all are familiar with these LED devices. These are nothing but optoelectronic devices which can emit different color lights. You must have seen many indicators constructed using LEDs. LEDs are available in different colors. Your 7-segment displays, your rolling displays, those are all using your LEDs. And nowadays we all are talking about LED bulbs. This is upcoming field of LEDs. So let us try to see what this LED is. Learning objectives of today's lecture are: understand the concept of light emitting diode, study working principle and characteristics of LED, know specifications of LED, specify applications of LED. You all are familiar with light emitting diodes, that is light as an indicator, or nowadays we have seen LEDs as light bulbs. These are nothing but PN junction diodes which emit lights when forward bias. Thus LED converts electrical energy into light energy. The arrows in the symbol, you can see they are pointing outwards, which indicates that light is emitted from the device. These LEDs are frequently used as pilot lights in electronic appliances as indicators. Here you can see different color LEDs: yellow LED, green LED, red LED, white LED, and this is also white LED, which is actually power LED, which is nowadays used in your light bulbs. Now here you can see each LED device is of two terminals. One is called as cathode and one is called as anode. If you observe it carefully, it is seen that there is difference between the length of these two terminals. The shorter one is the anode, shorter one is the cathode. Okay. Shorter one is called cathode, while longer one is called anode. Careful inspection also shows that near cathode there is flat surface over here, otherwise the other periphery of this surface is round. Now if you will ask me, if there is no difference between two lengths, if LED is cut by mistake, then how to find out which terminal is cathode and which terminal is anode? For that one has to use a multimeter. You know that in forward bias condition only LED emits light. In reverse bias it will not emit anything. So what I am going to do is use multimeter. I have put multimeter knob on diode terminal, diode testing terminal. Now if I am going to connect this positive to longer terminal and negative to cathode, you can see that light is getting emitted from the LED. That means now LED is in forward bias. That means this particular terminal is my anode terminal and this particular terminal is my cathode terminal. You can verify that if I reverse these two terminals, light will not be emitted. That means this is reverse bias of LED. So from this one can find out which one is cathode and which one is anode. Same you can see over here. This is reverse bias. This is forward bias. The most important part of light emitting diode is the semiconductor chip located at the center. The chip is made up of P and N type of semiconductors separated by a junction. Before learning LED working and fabrication, let us revise formation of PN junction of rectifying semiconductor diode. As seen in the diagram, during junction formation, electron starts migrating from N region to P region. In between, depletion region is formed. When depletion region is formed, it prohibits further migration of electrons between P and N region. During this process, some barrier or contact potential is developed. This contact potential depends upon what type of P material or N material is used for LED fabrication. Only when external voltage greater than this barrier potential is applied to any semiconductor chip, the current will start flowing and the electrons can cross the junction into the P region. Now let us see working of LED. It is slightly different from what we have seen in case of normal diode. LED works on electroluminescence principle, that is the process of giving light energy by an electrical voltage. In case of normal diode, the external voltage can create heat energy inside the diode, while in case of LED, the energy is in term of light. As seen, when LED is forward bias, electrons are injected into N region and holes are injected into P region. Both types of carriers start migration towards depletion region. During migration, electron-hole pairs are formed. Each electron-hole pair formation is radiative recombination, giving rise to photon emission. More the number of electron-hole pairs, more the number of photons emitted. Thus, light intensity is dependent on number of injection of electrons and holes, that is in turn on value of forward current flowing through the LED. This electroluminescence phenomenon can also be explained using energy band diagram. Normally, a semiconductor material has only a few thermally excited free electrons in conduction band and holes in valence band at room temperature. When an electron jumps from conduction band having higher energy level to valence band with lower energy level, an electron-hole pair is created. Energy is released in the form of photon. Wavelength of emitted light depends on forbidden band energy of semiconductor. The relation is given by Eg is equal to Hc upon lambda. That means lambda or wavelength of light emitted is equal to Hc upon Eg, where H is Planck's constant and C is velocity of light. Thus, one electron hole pair releases one photon of wavelength lambda is equal to Hc upon Eg. More electron hole pairs can generate more photons. This is possible by exciting electrons from external voltage source. Thus, it is nothing but electroluminescence principle, that is the process of giving light energy by applying an electrical voltage. It is seen that for different materials Eg is different and therefore lambda, that is wavelength, will be different. So different materials can emit different color light. Thus, to summarize, one can say LED is an optical source made up of semiconductors and converts electrical energy into optical energy. Now let us study characteristics of LEDs. Broadly, LED characteristics can be categorized as electrical and optical. Further, electrical characteristics are of two types: forward bias characteristic, giving relation between forward voltage and forward current, and secondly, input versus output characteristic. Optical characteristics are also of two types: spectral characteristic and special characteristic. This electrical characteristic gives how forward bias current increases with forward bias voltage. It is seen that there is sudden increase in forward current when voltage exceeds barrier potential. Note that LED requires greater than 1.5 volt for conduction. Here it differs from normal rectifying diode, which requires either 0.2 volt or 0.7 volt depending upon whether diode is germanium or silicon. Further, this voltage in case of LED depends upon which color, that is wavelength, is emitted by LED. It is seen from the characteristic that new voltage for the infrared LED is the lowest and it increases for short wavelength material. Once current starts flowing through the LED, it can only be controlled by a series external resistor. Since LED converts electrical energy into optical energy, light intensity variation with respect to input forward becomes important characteristic. The relation is linear. As forward current increases, light intensity goes on increasing. Spectral characteristic represents the light output versus wavelength. Spectral response of colored LEDs in visible range shows single peak occurring at corresponding color wavelength. For example, red color has peak wavelength as 640 nanometer while green has 530 nanometer and so on. Nowadays, you all have seen white LEDs in the market. These white LEDs emit wavelength covering whole spectrum. Spatial characteristic gives the radiation patterns of LEDs. It shows the spread of light output with respect to the space. In short, it gives directionality of emitted light. The graph shows typical radiation pattern of LED. The pattern depends upon the lens structure of the LED. The narrower the radiation pattern, the more the light is concentrated in a particular direction. Now let us study the fabrication of LED. LEDs are specialized form of PN junction diodes that have been designed to optimize their optical output. As a result, the LED structure and fabrication techniques need to ensure that electroluminescence is optimized. LEDs are basically consist of three main components. First one, actual PN junction chip, which is very important. Second, electrical contacts, and third one, transparent plastic encapsulation. The major part of structure is PN junction. Active films of the LED structure are normally grown epitaxially, often by liquid phase or vapor phase epitaxy. Common substrate used are compounds of gallium, arsenic and phosphorus. The PN junction can be created by either impurity diffusion, ion implantation, or it can be incorporated during the epitaxial growth phase. Once a shallow PN junction is formed, electrical contacts are taken out from both the regions. The junction is then encapsulated in transparent plastic medium. The plastic is molded into an approximate hemispherical shape. Other geometries are also available which improves the light emission direction and conversion efficiency from electrical to optical. Two basic configurations for the LED structure are surface emitting LED structure. Here, LED emits light perpendicular to the plane of the PN junction. And second, edge emitting LED structure. Here, structure emits light in a plane parallel to the junction of the PN junction. In this configuration, the light can be confined to a narrow angle. Light emitting diodes are available in a wide range of colors, with the most common being red, umber, yellow and green, and are thus widely used as indicators. The actual color of light emitted by LED is determined by the actual semiconductor compound used for fabrication. The different materials emit different wavelength of the light and hence different color. Commonly used semiconductors for LED fabrication are compounds of gallium, arsenic and phosphorus. Table shows the used semiconductor material to produce particular color. It is seen that for infrared color emission, gallium arsenide is used and wavelength of emitted light is 850 to 940 nanometer. For red color, emitting wavelength 630 to 660 nanometer, semiconductor materials used are gallium, arsenic 0.6 and phosphorus 0.4. For umber, the contribution of arsenic and phosphorus is changed. Here we have semiconductor materials as gallium, arsenic 0.25, phosphorus 0.75 and emitted wavelength is in the range of 605 to 620 nanometer. For yellow color LED, materials used are gallium, arsenic, phosphorus and nitrogen. Here wavelength of emitted light is in the range of 585 to 595 nanometer. Green has semiconductor materials as aluminum, gallium and phosphorus emitting in the range of 550 to 570 nanometer, while blue color LEDs use silicon carbide emitting wavelength 430 to 505 nanometer. White LEDs are using gallium, indium and nitrogen with wavelength 450 nanometer. Nowadays, OLEDs are available which are emitting in white color. From the above table, it is clear that the main P-type dopant used in the manufacture of light emitting diodes is gallium with atomic number 31, and that the N-type dopant is arsenic, atomic number 33. Other colors are produced by adding nitrogen or phosphorus impurities. Thus, one should remember that the color of the LED emitted by an LED is not determined by the coloring of the LED's plastic body, although these are slightly colored to both enhance the light output and to indicate its color when not illuminated. Most light emitting diodes produce just a single output of color light. However, multicolor LEDs are also available that can produce a range of different colors from within a single device. Most of these are actually 2 or 3 LEDs fabricated within a single package. While selecting an LED for particular application, it is necessary to comprehend the different LED specifications or LED parameters. LED specifications can be categorized as electrical and optical. Major electrical characteristics are as follows: forward bias current and forward bias voltage. Since basically LED is a diode, forward bias voltage and forward current are two important parameters. Low power LEDs are capable of driving forward current up to 100 mA, while power LEDs can have forward current as high as 1 ampere. Typical forward voltage drop varies between 1.2 volt to 3 volt. It is necessary to ensure that the maximum current rating is not exceeded. This could give rise to excessive heat dissipation within the LED chip itself, which could result in reduced light output and reduced operating lifetime. Reverse voltage. LED is not tolerant to large reverse voltages. They should never be run above their stated maximum reverse voltage, which is normally quite small. If they are, then permanent destruction of the device will almost certainly result. If there is any chance of a reverse voltage appearing across the LED, then it is always best to build in protection into the circuitry to prevent this. Normally, simple diode circuits can be introduced and these will be adequately protect any LED. Operating life. The light intensity of a LED does diminish gradually with time. This means that LED has an operational life. This LED specification is of particular importance when a LED or LEDs are to be used for lighting applications. It is not normally as crucial when the LED is used as an indicator. Here, a catastrophic failure is of greater importance. Operating and storage junction temperature. Normally, this temperature range is minus 40 degrees centigrade to 60 degrees centigrade. Thermal resistance, that means junction to ambient resistance. One should see that LED does not get heated too much, otherwise junction will be permanently damaged. In case of high power LED applications, especially heat sinks need to be used. Let us concentrate on optical specifications. Light output. The light intensity specification is not of crucial importance for most indicator applications, but with LEDs being used nowadays as for lighting purpose, this parameter has become very important. The light output from an LED is quantified as luminance intensity value and is expressed in millicandela or MCD. The luminance intensity value for an LED must be quoted for a given current. Many LEDs operate at currents of around 20 mA, but the light output of LED increases with increase in forward current. It is sometimes specified as radiation intensity at particular current in watt per steradian. Operating wavelength of LED. It signifies color of emitted light. In datasheet, directly numerical value of wavelength is given for color LED. In case of white LED, graphical spectral response of device is provided. Radiation pattern. It describes the relative intensity strength in any direction from the light source. Practically, light sources have various forms of radiation patterns based on different emission mechanisms, materials used for fabrication of sources, and manufacturing techniques. Datasheets of LED manufacturers provide radiation patterns in terms of relative intensity versus angle. The patterns may be symmetrical or non-symmetrical. In case of symmetric radiation patterns, manufacturers mention view angles. Now let us see some applications of LED. The LED is attractive in many electronic gadgets because of its low cost, simple structure and rugged features. Its application areas are as an indicator, as an optical source and as a light bulb. Now let us study these applications one by one. LED as an indicator. LEDs that produce visible radiation are useful in instruments, calculators and so on for display purposes. Various forms of LED as an indicator are: one can use simple LED, 7-segment displays, dot matrix displays and bar graphs. You can see here, this is simple red LED used as an indicator. This is 7-segment display where actually 7 LEDs are constructed in particular fashion. If this particular 7-segment display is capable of showing letters or numbers from 0 to 9, you can see the image where according to our requirement any one particular LED can be glown and any number can be displayed on display. If we want further clarity, then we should go for dot matrix array. Here you can see different sizes of dot matrix array where number of LEDs are constructed in rows and column fashions. This is another kind of LED indicator which is called as bar graph. In first bar graph, you can see same color LEDs arranged in one particular column, while in second bar graph, different color LEDs are used. Here you can see applications, areas of bar graphs. You can see different bar graphs, first with 10 LEDs, 20 LEDs, 25 LEDs, 50 LEDs and so on. Using such different number of LEDs, the LEDs can be used for graphic displays. LEDs which are shown in all these fashions, each LED here in this case is operated in forward bias condition. Normally one simple series resistor is connected in series with LED. Normally LED requires 1.5 volt to 2.5 volt for its operation and current flowing through each LED should be 10 milliampere. To prevent overloading, normally resistor of 470 ohm is connected in series with it. Now let us see how LED can be used as an optical source. First let us see how it is used as an optical source in optical communication. One of key components in optical communication is the monochromatic light source. In optical communication, light sources must be compact, monochromatic, stable and long lasting. Therefore, LEDs can form continuous wave light source for optical communication. The LEDs used in communications are constructed to allow light to emerge from the device edge. Another useful application of LED as optical source is in optocoupler or optoisolator. Optoisolator is nothing but optical source and optical detector combination. Advantage of optoisolators is that it provides electrical isolation between two circuits while connecting two circuits optically. Most of the time, we will find the applications of optoisolators where IR LED and IR detector pairs are used. You all are familiar with this device. Yes, this is nothing but LED tube light. LEDs are gaining widespread acceptance as the most efficient light sources due to its advantages of low power consumption, long life, more reliability, small size, lightweight, and above all, it is eco-friendly. And therefore, nowadays it is found that LEDs are replacing incandescent and your compact or CFL bulbs. So to summarize, we have seen that LEDs are optoelectronic devices which converts electrical energy into optical energy when forward bias. When LED is forward bias, basically electrons are jumping from conduction band to valence band. In this process, electron hole pairs are created which are giving rise to one photon creation. More number of electron hole pairs, more number of photons will be emitted. Thus, LED intensity output is dependent on how much forward current is flowing through LED, or in turn what is your forward voltage applied, external voltage applied to it. For different color emission, it is seen that materials used for LED fabrications are different, because in this case energy band structure will be different and wavelength emitted, that is lambda, will be different. There are many applications of LEDs which are commonly seen in day-to-day life. LEDs are normally used as an indicator, or it may be used as an optical source in optical communication or in optoisolators. Nowadays, we all are familiar with LED application as illumination device. LED bulbs are capturing the world and they are replacing incandescent bulbs and CFLs. Thank you.